Good morning, students. So, as we discussed in the last lecture, today we are going to talk about a few special types of graphs. So, the first in this list is what we call a null graph. So, as the name suggests, okay, null graph is a graph that contains only isolated vertices. That is, the set of edges is null here. Okay, so an example could be a graph like this. The next in this category is a complete graph. So a simple graph G is said to be a complete graph if every vertex in G is connected to every other vertex by an edge. So sometimes these graphs are also called cliques. And some of the known complete graphs which come handy in various applications, as we will see in higher graph theoretic courses, are K1, K2, K3, K4, K5. So they look as follows. K1 is a single node, K2 is an edge, K3 is a triangle, this is K4, and this is K5. So you see, in each of these, okay, every node is connected to every other node by an edge. In each of these graph, say for instance, let's take K4, this node here, A, say call it A is connected to B, C, D, all the other nodes in the graph by a direct edge. Okay. So similarly for K5 and all other such cliques. So in general, we will refer to a clique of n nodes by Kn. Okay. So a very easy thing to see is that number of edges in Kn is nothing but nc2. Okay, all pair of nodes are connected. So that is, and this you can verify with the examples that we have drawn here. The next in line is a regular graph. A graph in which all vertices have exactly the same degree is called a regular graph. So say if the degree of every node in the graph is R, then the regular graph is denoted by R. So looking at the last two special type of graphs, we can always say that Kn is a regular graph. Okay, and R in a regular graph like Kn is equal to n minus 1, because every node in a clique of size n of order n will have degree n minus 1. Bipartite graph. So in a connected graph, if the vertex set V can be partitioned into two disjoint sets, let's call it V1 and V2, such that edges run from nodes in V1 to nodes in V2, but never within nodes of V1 or within nodes of V2 is called a bipartite. So as if the graph is creating a bipartition, partition of the nodes into two different sets, such that the edges only run between these two sets but never within the individual sets. So an example of a bipartite graph could be like this. You have A, B, C nodes, you have D, E nodes, and you can have something like this. So this is a bipartite graph of 5 nodes which have been partitioned into 3, 2. The next thing that we need to discuss about are subgraphs. Now again, as the name suggests, let us say G and H are two graphs with vertex sets VG and VH, okay, and edge sets EG and EH. If VH is a subset of VG and EH is a subset of EG, then we say that H is a subgraph of G. So that means if H is a subgraph of G, then all vertices and edges in H are also present in G. Now, if VH is equal to VG and EH is a subset of EG, then H is called a spanning subgraph of G. That is, the vertex set is same for the two graphs. However, the edge set is such that a set of a sample of edges from the graph G is present in the graph H. Okay. Similarly, if and then H is called an induced subgraph of so for the vertices in H. So if now the vertex set of H is a subset of G, however, all the edges that were present in G are also present in H for this particular vertex set VH, then H is called an induced subgraph of G. So for instance, if we take an example, so if this is G, then AFB is an induced subgraph of G on the vertex set ABF. So you see, this is a subset. ABF is a subset of vertices of all the vertices present in G. However, all the edges that are present among A, B, and F in G should also be present in this induced subgraph. Okay, so then this kind of graph or a subgraph is called an induced subgraph. So the next thing is how to represent a graph. So there are at least two different ways in which one can represent a graph. Okay. The first of this is a matrix representation. This is also sometimes called the adjacency matrix of a graph. So again, since we have two different types of edges, depending on whether they are undirected graphs or directed graphs. So the adjacency matrix definition also will have slight changes. So adjacency matrix for undirected graph. If an undirected graph G consists of n vertices, assuming G does not have any parallel edge, then the adjacency matrix of G is an n cross n matrix represented as such that Aij is equal to 1 if there is an undirected edge between vertices Vi and Vj, and is 0 if there is no edge between Vi and Vj. Similarly, we can extend this definition for directed graphs. So if a digraph G consists of n vertices, then the adjacency matrix of G is an n cross n matrix such that if Aij is equal to 1, if there is a directed edge from vertex Vi to vertex Vj, and 0 if there is no edge from Vi to Vj. Now the next type of representation is a linked list representation. This is also called the adjacency list. So in this representation, each node U in the graph contains a linear linked list consisting of vertices directly reachable from U. So if there are n vertices in G, then there are n such linked lists. So if we have a graph like this, then the adjacency matrix corresponding to this graph looks as follows. So this, you read it as follows. There is no edge from node 1 to 1. There is an edge from node 1 to 2, and therefore this cell is 1. There is an edge from node 1 to 3, and therefore this cell is 1, and so on and so forth. So the list representation of the same graph is as follows. So this is the head node in each case, and there is this linked list of connected vertices. The last thing that we need to discuss is the incidence matrix representation. So in this representation of a graph, the matrix is defined as follows. Aij is equal to 1 if the jth edge Ej is incident to the ith vertex. Otherwise, it is 0. So let's take an example and understand. So let us say we have a graph like this. So the edges here also are labeled. Okay, note that the edges are also labeled alongside the nodes. Now the incidence matrix for this particular example graph is written as follows. So we question whether the edge E1 is incident on the node A, and we get an answer yes, and therefore it's a 1. E2 is not incident on A, hence 0. E3 is not incident on A, and hence 0. On B, all the 3 edges are incident. On C, E1 is not incident, however E2 and E3 are both incident. Okay, and this constructs the incidence matrix of the graph. So we will stop here. I would request you to go through the previous day's lecture and today's lecture in details so that you can easily follow the next set of lectures, which will be on graph algorithms and in specific traversal on graphs.